0.620 micrometers, and the red color or the red spectrum that can be observed if the wavelengths are going to be of in the range of 0.620 to 0.7 micrometers. So this is about the visible spectrum. Now talking about the next, that is about the infrared. Again, this infrared spectrum is going to be considered as an useful in the terms of remotely sensed data. Next portion of the spectrum which is of interest, that is nothing but the infrared. That is going to cover the wavelength ranging from approximately 0.7 micrometers to the 100 micrometers or more than that. So this infrared regions that can be divided into two important categories as the reflected infrared and emitted, or it will be considered as a thermal infrared. So these reflected or the thermal infrared, these are going to be used for the various purposes. So radiations in the reflected infrared region, these are going to be used in the remote sensing purposes in various in the various ways which are similar to the radiation in the terms of visible portion. And the another one, that is nothing but the uh, reflected infrared or reflected infrared waves. These are going to cover the range of 0.7 micrometers to the 3 micrometers. So these particular thermal infrareds, if you are going to talk about the another one, that is the thermal one. So thermal infrared regions, these are quite different than that of the visible and the reflected infrared portions, as this particular energy is essentially the radiations that is emitted from the earth's surface in the form of heat energy. So the thermal infrared, these are going to cover the wavelength approximately from the 3 micrometers to the 100 micrometers. But for the remote sensing applications, we are basically going to focus on the reflected infrareds. These are going to be useful. The next portion after this infrared that is of interest, that is nothing but called as the microwave. So the portion of spectrum which is again a next category, this is also going to be considered as a useful for the remote sensing data. The various sensors in the microwave region, these are going to be used. So this is going to range from the 1 mm to the 1 meters wavelength. So this is going to cover the longest wavelength which is used for the purpose of remote sensing applications. So shorter the wavelengths, these are going to have the properties which are similar to the thermal infrared region, while longer the wavelengths, these are going to have the approach of wavelengths used for the radio broadcasting. Now talking about the next part, that is the second principle, which is called as the interaction with the atmosphere. Till now we have discussed about the source, that is the electromagnetic waves and electromagnetic spectrum. In detail we have discussed. Now the second thing, we are supposed to talk about the interaction of these electromagnetic waves with the atmosphere. So before these radiations which are going to be used for the remote sensing, these are going to reach to the before it is going to reach to the earth's surface, these are going to travel through the earth's atmosphere for a particular distance. So atmosphere, we know that this is going to be consisting of the various particles as along with the gases. So these particular particles and the gases which are present in the atmosphere, that will be going to interact with these electromagnetic waves, and this is going to have an effect on the electromagnetic waves, and this is going to cause the process or this particular the mechanism of this particular light, which is falling in the category of scattering or the absorption. A part of light may get scattered, or part of, sorry, not the light, part of the waves that may get scattered, or part of the waves that may get absorbed in the atmosphere. So we need to understand about this scattering and the absorption. What is the meaning of scattering and what is the meaning of absorption? So scattering is what? Scattering, it is going to occur when the particles or the large gas molecules which are present in the atmosphere, it will be going to interact, and that is going to cause the electromagnetic radiation to be redirected from its original path. It is going to be redirected from its original path. So it is going to be considered as an scattering. How much scattering takes place, that is going to be completely depending on the various factors that may include the wavelength of the radiation and the abundance of the particles which are present or the gases which are present into the atmosphere. Along with that, how much distance these electromagnetic waves these are going to travel into the atmosphere. This is also one of the factors in which the scattering is going to be depending. In this figure, you can able to see the process of scattering, that is in this particular depth of an atmosphere, how these particular waves are getting scattered. The second thing or the second concept that you need to understand, that is about the absorption. So it is another main mechanism that we can say about the electromagnetic radiation. So when it is going to come in the contact with the atmosphere, it will be going to interact with this, and in this particular process or in this particular phase, the part of the waves which are getting scattered, some of the particles or some of the waves, they are getting absorbed. The phenomena that causes the molecules in the atmosphere to get to absorb energy at various wavelengths, this is nothing but the process called as an absorption. So ozone, carbon dioxide, or the water vapors, these are the main components. These are considered as an atmospheric constituents. These are going to absorb all these radiations which are reaching to the earth's surface. So when these electromagnetic waves, these are going to come in contact with this particular atmosphere, these two important mechanisms, these are going to operate in the terms of scattering or maybe in the terms of absorption of these particular waves. Now you are supposed to understand one important terminology with respect to this phenomena of scattering or the phenomena of absorption, that is nothing but called as a atmospheric window or atmospheric windows. So what is the meaning of atmospheric windows? So when these particular waves, electromagnetic waves, these are getting absorbed, this electromagnetic energy, if it is getting absorbed at various, we can say the various spectrums or the various regions or the specific regions of the spectrum, these are going to influence a spectrum that can look like that can look for the remote sensing purposes. So this particular region or this particular spectrum, that is going to be considered as an atmospheric window. So the areas of the spectrum which are not severely influenced by the atmospheric absorption, and thus it is useful for the remote sensors, this is going to be considered as an atmospheric windows. So you have to remember this particular terminology. This is very important part. You need to understand what is the meaning of atmospheric windows. So in this particular diagram, you can able to see, as shown in this particular figure, the portions that have the high transmissions are the atmospheric windows. Here it will be considered as an atmospheric windows. Fine. Now the next thing is that you need to understand about the concept of radiation. That is nothing but the third principle, that is target interaction. When these electromagnetic waves, these are going to reach to the ground surface, it will be going to interact with the various objects as well as the earth surface. So there is a process which is called as an radiation that you need to understand. So radiation that is not absorbed or not scattered into the atmosphere can reach to the earth surface and interact with the earth surface. So there are various forms that you need to understand in the terms of radiation. When the radiation is going to take place, how the energy is getting transformed. So this particular energy will be going to transform in the form of incident light or the incident upon the surface when it is going to fall. So absorption may take place, transmission may take place or reflection may take place. Okay, so absorption is denoted by capital letter A, transmission is by capital letter T, and the reflection by capital letter R. So this absorption, which is going to occur when the radiation or the energy which is absorbed into the target. Suppose consider there is a building which is present on the earth. Now a part of some components of this particular building, like the glasses are there, the window glasses or the door glasses or some roof panels are there. These are going to absorb some sort of energy that may get converted into the various ways. Like you are feeling the heat waves. The heat is nothing but again a part of your uh, electromagnetic energy. It is getting converted to the another form, but it is a part of your radiation. When it is going to fall on the any particular object, part of the energy it will be getting radiated back, or it will be getting absorbed. The next thing is nothing but the transmission, capital T, which is going to occur when the radiation passes through the target, and the reflection, capital R, that is going to occur when the radiation bounces off the targets and it is redirected. Okay, so in this particular diagram you can able to see this is the incident light, which is denoted by capital I. This is, we can say, like electromagnetic waves coming from the sun. So in this absorption, okay, part of these waves, these are getting absorbed into this particular leaves. Okay, this is absorbed in this particular target. So this energy is going to be useful for, say, maybe for the photosynthesis purpose. So this is, we can say, the part of your absorption. Part of the light it will be getting transmitted. If you look at this particular leaves, and from that leaves if you are looking towards the sun, so you might see like part of the light that is going to reach to your eye. Okay, so that is going to be considered as a transmission. So waves, this particular wave, these are getting completely transmit from this particular leaves. So this is a transmission process that is going to occur when this radiation, these are going to pass through this particular target. Next thing is that reflection, denoted by a capital letter R. This reflection occurs when the radiation is going to bounce off from the targets and may get redirected. So here you can able to see a part of the light or the part of the waves that will be getting reflected back, that will be getting bounced back. Okay, so when any particular light it is going to fall on the any particular object, these are the three processes these are going to take place. These are nothing but called as absorption, transmission, and the reflection. Now again, there are various types of reflections. Okay, basic two types of reflections that we need to understand. In remote sensing, we are interested into the radiation which are reflected from the targets, not about the transmitted or the absorbed energy, but we are interested only in the terms of energy that will be getting reflected back from the targets. So this particular reflected energy, that is of two types of reflections that we need to understand. These are going to represent the two extreme ends of the way in which the energy is reflected from the targets. One is called as specular reflection, another one is called as a diffused reflection. So what is the meaning of specular and what is the meaning of diffused? So when a surface which is of smooth, a very smooth surface, like a mirror. So when the reflection which is going to take place from such a smooth surface, the energy which is directed, that will be completely directed away from the surface in the single direction. That is called as a specular reflection. Another one is nothing but the diffused reflection. So diffused reflection occurs when the surface is rough and the energy is reflected almost uniformly in all the direction. Okay, now just take the examples of the specular and the diffused reflection. Say there is a water body. Okay. Now when this incident wave, these are going to fall on this water body, maximum, or we can say the 99% of the waves, this will be getting reflected back. So this is, we can say, the best example for the purpose of the specular reflection. Or maybe if you are going to consider the very smooth surface roads where there are very less undulations, or we can say a very smooth surface is there, in that case maximum of the energy that may get reflected back. So that is, again, we can consider the example of a specular reflection. But if you are going to talk about the diffuse reflection, so you can take the example of a uh, road surface again, but which is not a we can say the plane as, or as smooth as the maximum of the light that may get reflected back. But we can say the like rough roads, or maybe in the terms of village roads, we can say when the right light is going to, or these particular waves are going to fall, part of the energy that may get diffused into the road and part of the light may get reflected back. So that kind of example you can consider under the category of diffused reflection. Okay, so there are two types of reflections, specular and the diffused reflection. Now here we are going to take the example when the this particular electromagnetic waves, when these are going to fall on any particular object on the ground, so how it will be going to interact. Just in the last slide we have discussed about the example of leaves, absorption, transmission, or the reflection. So when this particular light, when it is going to fall on the any particular object, how it is going to behave. As we are talking about this water resources engineering course, so we are going to come in across with the land use and the land cover information. Okay, land use land cover, it is going to talk about the green cover. So green cover refers to what? Green cover refers to the trees, plants, grass which are present on the earth surface. That may be a part of your forest area, that may be a part of your farm areas, or maybe a component where you are planting the trees at your home. So all these green cover, we can say a part of your greenery, that we need to understand how the waves are going to interact with this green cover. So here we are taking one example of leaf. When the light or this particular electromagnetic waves, when they are going to fall on the leaves, how it is going to behave, or how it is going to be studied, or how it is going to be useful for the purpose of preparing or analyzing the data for the remote sensing applications. So you might be aware of this leaves, so which is consisting of some chemical compound which is called as a chlorophyll. So this particular chlorophyll, that is strongly absorbing the radiations in the red and the blue wavelengths. Okay, in the red and the blue wavelength, these are going to be absorbed, but it is going to reflect the green wavelength. Remember this thing, what I'm talking about, the chemical compound which is present, this is nothing but a chlorophyll. This chlorophyll, this is strongly absorbing the radiation in the red and the blue wavelength, but it is reflecting the green wavelengths. Now leaves, these are going to appear the greenest to us in the summer when the chlorophyll content is at the maximum. Reason is that the chlorophyll is going to reflect this particular energy completely. Red and blue, these are going to be absorbed. If you remember, I told you this RGB band, Okay, three color RGB, red, green, blue. So out of this red color or the blue color, this is absorbed by these leaves, which is consisting of the chlorophyll. But the green color, that is completely reflected back. Here in the second diagram you can see these infrared, red, green and the blue. These are the, we can say, the various types of wavelengths these are going to fall on the leaves. Out of that, blue and the red, that is getting absorbed, and the green and the infrared, these are the two waves, these are getting reflected back. Okay, that is going to happen only because of this chemical compound, that is nothing but the chlorophyll, which is present into the leaves. But this is going to be observed during what? During the summer season. But in the autumn season, when there is less chlorophyll in the autumn, the leaves, so there are, we can say, the less absorption is going to take place, and proportionately more reflection of the red wavelength. Now here, when the plant is completely green, in that case maximum of the green wave, that is getting reflected back along with the infrared. But when the leaves are dried up or less amount of green colors, in that case the absorption of this red band is getting reduced, and in that the red wavelength is again getting reflected back and making these particular leaves, which are supposed to appear like a red color or the yellow color. So yellow is the combination of nothing but the red and the green wavelengths, that you are aware of. This combination of colors, when the red and green are mixed together, it will be denoting the color of yellow. So when the red color is again getting reflected back, so in that case we'll be going to see the plant leaves which are of not in green color, or you can say the, in the during the autumn season, the maximum of the energy that is getting absorbed, sorry, reflected back due to the lack of chlorophyll. So the internal structure of the healthy leaves act as an excellent diffuse reflectors of nearly infrared wavelengths. Okay, nearly infrared wavelengths. So this particular study, what it shows, the study shows that these various wavelengths which are falling on any particular object, here we have considered the object of leaves, plant leaves. You can also consider the example of water. Okay, you can also consider the example of water. Here we have considered the leaves. So depending on the chemical compound which is present, we have discussed about the phenomena of absorption of the energy or the reflection of the energy, and based on that we can able to classify the leaves in the various seasons. In a similar platform, you can also have the example of water. Say like longer wavelengths which are of visible or the nearly infrared radiations, it will be getting absorbed more by the water than the shorter visible wavelengths, and that is the reason that water that looks in a blue color or the bluish green color due to the stronger reflection at these shorter wavelengths, and darker if it is viewed at the red or the nearly infrared wavelengths. If there is a suspended sediments which are present into the water, the upper layer of the water body, then this allows the better reflectivity and a brighter appearance of the water. So the appearance of this particular water, color of the water, it shows a slight shift to the longer wavelengths. So this, any particular impurity, just like here we are talking about the suspended sediments, that can be easily considered as an confused with the shallow or the clear water. But this phenomena appears to be very similar. The reason being, here also, if you are going to talk about any particular water body, we are having the some green plants present into the water bodies, and like algae or some other water aquatic plants, these are also going to be consisting of some chlorophylls into it. Again, these are going to absorb the wavelengths which are falling on it and reflecting some component of the energy back, and this reflected energy is going to be used in the terms of determining the vegetation index. So you may came across with the one important term which is called as a NDVI, that is going to be called as a normalized difference vegetation index. That is going to give us the idea about the how what is the index coefficient that is going to vary in the terms of vegetation all over this particular area which is of interest for the study. Again, this is the part of your study where various bands, RGB bands, these are taken into consideration for the sake of understanding the concept or understanding the visibility of the green cover on the present on the earth surface. So how to calculate normalized difference vegetation index? Again, for that purpose we are having one small assignment that we are going to discuss through a video demonstration about calculation of normalized difference vegetation index. Fine. Okay, so this is what up to the principles of the remote sensing, what we have discussed till now. The next topic that we need to discuss, that is about the integration of the remote sensing with the geographic information system. Okay. So up to this, any question or any point which is not understood to you? Many of the things are very basic things that we have just revised quickly. So in a minute we will be going to continue with the second point of interaction. Till that, if you have any questions, you can unmute and ask the questions. Okay. So let us continue with the next topic for the discussion, that is the interaction or the integration of this particular remote sensing with the technique which is called as the geographic information systems. So all of you are aware of this particular term, heard many of the times, called as the GIS. The GIS is what? GIS refers to the geographic information system. It is the system that is designed to capture, store, manipulate, analyze, manage, and present all the types of spatial or the geographical data that will be in the digital format, that is called as a geographic information system. Now the data which is captured by the remotely sensed technique, this particular data that will be stored in the form of digital image, which is a part of your geographic information system. Okay, so the data capture, that is entering information into the system and digitization. These are the two important steps in the GIS. So information which is captured by the remote sensing, or we can say the sensors which are located into the satellites, this electronic information we have to feed to generate the images, or to represent the information in the form of images. So here, whatever the electronic information that is collected, that will be represented in a digital manner with the help of technique called as a digitization. So digitization is what? Digitization is again a technique where we can say we are going to group together various kinds of elements which are having some particular kind of a magnitude captured by, or which is sensed by the sensors, that we need to collect together, and we have to mark it separately as a part of digitization. So digital image, where we can say like a digital information can be stored into the image, that will be a part of digitization technique. Okay, so two basic steps: entering the information into the system, and digitization, where digital information that can be uploaded in the form of digital images. So this particular GIS, there are various ways to capture this particular data into the GIS. So existing data printed on the paper or the topographical maps, it can be digitized or scanned to produce the digital data. Now what we can do, we can just take an example of any particular topo sheet. Now topo sheet, it will be consisting of various information about the topography of that particular locality. Like we can say we are having the contours, we are getting the regions of the hilly area, the information about the ponds, lakes, reservoirs, rivers. So this particular data which is present in a topographical sheet or the topo sheets, this particular topo sheet we can scan. Okay, we will scan this particular topo sheet, and this scan topo sheet we can use as a reference to demark all these features which are present on the topo sheet, like contours, some water bodies, some forest covers, etc. So this particular data, it will be used for the generation of another image that will be in a digital format, that will be considered as a one way to develop the digital information, to convert the digital information. Okay, so printed data, hard copies of the topo sheets, these are converted into the digital form by applying, by plotting that particular object boundaries and allocating some specific values to that particular information. That will be a way of generating the digital data or the digital image, that is again in the format of GIS. That is the one way. Another way is that survey data. Now you have studied about land survey in second year. You have carried out the project about the alignment of a road, right? So this particular data which is collected by the total station, this particular data that can be entered into the geographical information system from the digital data collection system or the survey instruments. Now the total station which you are going to use, this particular data that is stored into this total station, that can be transferred digitally to the laptops or the PCs, and through that the information that can be transferred to the softwares which is having a use, or we can say the application where we can convert the data that will be in the digital form, image formation. This is another way to develop the GIS information, or maybe in the terms of developing a GIS data in a digital format. Third way. Now what is the third way? you have studied again about the aerial photography. Okay, the recent example of aerial photography that you might be aware of, that is nothing but the drone, right? So the drones, this is the recent example of the aerial photography. But if you see the study of the aerial photography, it is going to start with the birds. So you might have heard about the bird eye view. Bird eye view. So when the birds, these are going to fly in the sky, along with the birds there was a short camera, there is a small camera, it was tied into the uh, tied with the birds, and this is going to capture the information on the land surface as a part of bird eye view. That was the very historical moment, we can say the history in which the aerial photography was started or the initiated. Then we were having the balloons. So through balloons, the photography which is collected in the digital format, that is a part of again aerial photography. Hot air balloons were used most of the times in the terms of collecting these aerial images. Then we were having some aircrafts or the choppers. Through them also we were using these instruments, or we can say the aircrafts or the choppers, to collect the information about the land from a particular height. So that is a part of your aerial photography. And now the recent one is nothing but a drone surveying, that is emerging field in the part of digital data. So this aerial photography is the source of collecting the information and identifying the attributes which can be mapped in the layers. So various types of information that is going to be collected, these attributes, this can be used for locating the various parameters present on the earth surface. So this is the third way by which we can capture the data and convert it into the digital GIS form. The last one is, or the fourth one, we can say the remotely sensed data in the data collection method, that is consisting of the sensors which are attached to the platforms. So the satellites, these are going to be including the various kind of sensors, digital scanners, lidars. These are the platforms which are mostly consisting with the satellites or the aircrafts. So remotely they are going to capture the data. This particular data is transferred to the ground receptors and they are going to convert this data into the digital format. So these are the four possible ways by which we can capture the data and convert it into the GIS form. Okay, so here we can say an integration of this remotely sensed information in the form of converting the data into the digital format as a part of geographic information system. So first thing we have discussed about the converting the topo sheets image, topographical image, hard copy into the digital format. That is the one way. Second way is the survey information, the land survey which you are going to carry out through the various instrument that can be used for the collecting the information and converting it into the GIS format. Third option we have, or the third way we have discussed, that is about the aerial photography, hot air balloons, aircraft, choppers, then drone surveying. These are the part of your aerial photography. This can be also a part of your remote sensing information and converting it into the geographic information part. And the last one is nothing but the satellites. So satellites which are having the various kind of sensor, these are going to capture the information and that will be going to be converted into the digital formats. And again it will be having an, we can say that the integration of this remotely sensed data in the format of geographic information system. Okay, so I hope you have understood about this integration, how it is going to take place with the geographical information system. So thus the integration of remotely sensed data and geographic information system, it occurs naturally, and this is desirable for the effective utilization of the vast magnitude of the spatial data accessed through the remote sensing. So an important feature of this geographical information system is that its ability to overlay spatially georeferenced data into the layers. Now here you are coming across with the one important term which is called as the georeferenced. Now what is the meaning of this georeferenced? So you are already aware of this coordinate system, right? So universally accepted coordinate system, that is Universal Transverse Mercator, UTM. This is going to be considered most of the time for the purpose of providing the reference for that particular data which is captured by the remote sensing. Now consider one particular locality like our campus. So our campus is going to have some coordinates which are assigned to this particular location. So when you are going to collect the information through the satellite, and it will be going to be converted into the digital format as a digital image, that particular digital image, when you are going to click on that particular image to the locality of our institute, you are going to get the coordinates of our institute location. So that coordinates, these are nothing but, we can say, a reference which is given to that particular point or that particular location. So this reference is nothing but called as a georeferencing, which is nothing but going to deal with the coordinate system. So whatever the universally accepted coordinates, geo coordinates are there, these are assigned to the image, digital image. This is nothing but considered as a georeferencing information or the georeferencing data, and this is possible with the GIS technology. So important features on which are present on the ground, like various locations are there, all these are marked with the geo coordinates, and that's why the data which we are getting, that we can overlay each other. Like if you wanted to have the study of various data like soil data, or we have to carry out the study of topographical data, we are supposed to carry out the information about the land use land cover data. As these images are geo-referenced, we can overlay them over each other. Okay, just like you can consider the example of, say, we are having the one information about the we can say the terrain, various information is there. So over this particular image we can overlay the another information, like over the terrain data we can overlay the information about the soil parameter. Over that terrain and the soil we can overlay the information of the land use and land cover. Over this information we can provide the information about the various land use parameters or any other parameter which is of use. So overlaying of various information for the same reference point, that is possible only by the means of georeferencing, and that is possible with the feature of geographic information system. So this georeferencing is very important part, and this georeference image that we can get by the means of geographic information system. So this enables the users to separate the structures and objects such as the stream networks, land use patterns in the layers to determine how they are going to interact with each other. In many of the instances, the remotely sensed data that are not sufficient for the hydrological purposes, but similarly these particular GIS based data, like the data of the soils, data of the topography, data of the elevations, these are of not adequate for the hydrological study, but along with that some other parameters, these are also required to be studied. Like along with the topography we are going to require the information about the hydrological parameters. Along with that we are going to require the meteorological, that is nothing but the climatological parameters, and combining or integrating this all the data with the remotely sensed data with GIS technology, that will be going to complete the study of the hydrological parameters. Like if you are going to consider the hydrological cycle, so hydrological cycle that you have studied from your school days, just studied about the water, how it is going to be transferred in the system. But when this rainfall, it is going to fall over the earth surface, it will be going to transfer in the different modes. Part of the water that will be getting absorbed into the atmosphere, part of the water will be present on the earth surface, part of the water may get it will be getting infiltrated into the ground surface. So what are the parameters based on which the infiltration is going to take place? What are the parameters on which evaporation is going to take place? What are the parameters due to which the water is going to flow over the ground surface? So these are going to talk about the hydrological parameters, meteorological parameters, soil parameters, then underground aquifers are there where the groundwater movement is going to take place. So all these parameters are need to be taken into the consideration. Then and then only we are able to carry out the study of hydrological models. So combination of all these information along with the remote sensing data, this is going to make the sense in the terms of developing the hydrological models which are beneficial for the purpose of hydrological studies. So combination or combining or integrating the remotely sensed data with the GIS data, these are going to enhance the capability for undertaking the hydrological analysis and the modeling parts. So for that purpose, this integration of the remotely sensing data in the terms of GIS is going to be considered as an important part. One inherent problem in the integration is that the remote sensing that is going to use a raster or the grid based formats for the data collection. This is the important thing. Now you have studied about the raster format and the vector format data. Raster is what? Raster is nothing but the, we can say, the grid based format. You are capturing the photographs from your mobile phone. Okay, it is going to show you, if you see the details of that particular image, you will able to see the resolutions. So resolutions are what? These are nothing but going to give you the grids, how many number of grids, that pixel, these are present into that particular image. That is going to give you the resolution of your image. So depending on the number of grids, smaller grids, the resolution of image is going to get enhanced. The maximum number of pixels refers to what? Maximum resolution and the maximum, or we can say the very good quality of that particular image, right? And if the number of pixels are less, in that case you are going to have the little bit blurred, or we can say image which is not much clear. So this grid based format, that is having a pixels, this is nothing but for the format which is called as a raster data set or the raster file format. So when the remotely sensed data is the data which is remotely sensed by the satellite, that is always represented in this raster format, that is nothing but the grid based format. Grid based format means the pixels format, but this is for the data collection and the acquisition. But when you are converting it into the GIS format, the GIS information system, that is going to have the information in the vector format. So vector format is what? Vector format is going to be represented in the three important parameters. Okay, here we have discussed about the first, nothing but the raster format. So the former format, that is information that is stored as a collection of a picture. These are elements, nothing but the pixels, each holding only one value. Means what? When say this is what the digital image is there, which is say raster format, okay, which is of various grids. Okay, say like these are the grids or the pixels. So each pixel, this particular one pixel, is going to have the information stored into that particular pixel. say like elevations are there. You have studied about the topo sheets. Okay, so if elevations are there, so what is the elevation in this particular area? So that average elevation value can be stored into this pixel. That is nothing but your raster format. But what is the vector format? So vector format is nothing but the format where we can have the representation of the data in the three aspects. These are nothing but the points, lines, or the polygons. So in your image, some locations are going to be represented by the points. So like we can say the location of the any particular building, it can be represented by a point. If you are having say river or the roads, this we can represent by plotting or drawing a line. Or say any particular water body is there, say reservoirs or the ponds or the lakes, that we can draw a polygon to that. So these are the three different ways by which we can represent the data in a digital format. So this particular data, that is going to be considered as a vector file format. So I hope it is clear to all of you what is the meaning of raster data and what is the meaning of vector data. So vector format is the data that are collected for each feature that is represented as a point feature, line feature, or the polygon feature, and the digital representation of line and the polygon that is consisting of an order of sequence into the x and y coordinate pairs. So all these features that we can represent and we can assign the values to them in the format of vectors. Okay, so here again we can have the conversion of raster data into the vector data, where we can have an integration of this remote sensing information, remote sensing data in the format of digital images as a part of geographic information system. So raster to vector conversion, again it is a part of integration of remote sensing and the GIS applications. So in the recent years, many geographic information systems, they have adopted the raster formats like ArcInfo, ArcGIS. These are some of the softwares. They have adopted the raster formats for the processes, but not all the softwares, and some of the other softwares like GRASS, these are going to offer both raster and the vector data analysis capabilities. In such systems, the integration of remotely sensed data and the GIS is very easy. So you may be going to come across about one elective course in the next semester, that is nothing but the QGIS, quantum GIS, where we are going to see this particular process in detail about how we can use this remotely sensed data in the format and how we can convert it into the geographic information system, that is into the raster file format, sorry, vector file format. So here it is the discussion about integration of remote sensing with the GIS technology. Now the next point which we need to discuss, that is the remote sensing of hydrological elements. So as I told you, in the water cycle, that is hydrological cycle, when we are going to have the study of any particular hydrological parameters, this remote sensing is the very important technology that is taken into consideration for these modeling parts or the analysis of any hydrological parameters. So for that purpose, we are supposed to require the various data sets or various informations. So how we can collect this data, or remote sensing, can we make the use of this remote sensing in the terms of collecting these hydrological parameters? So the answer is yes. At some extent, some of the parameters are collected directly, but for some of the parameters, we cannot get the information directly, but we have to rely on some of the other informations, and from that we can collect the information about these hydrological elements. Just like evaporation, we cannot calculate the evaporation directly, but evaporation is going to be depending on what? Evaporation is going to be depending on various parameters, like Evaporation is going to be depending on the soil temperature. It will be depending on the surface temperature, soil moisture, vapors which are vapors concentration, then radiation, air temperature, etc., or the aerodynamic resistance. So if we are able to collect these parameters, from that also you can relate at what rate water evaporation may take place. So some parameters like rainfall, definitely we can able to calculate it directly by the means of another some techniques, but some of the hydrological parameters are there in such a way that we cannot capture or we cannot correct the information directly, but we have to rely on some other information from which we can carry out the information or we can collect the information about some hydrological elements. So we will see one by one in detail about these various hydrological parameters and how we can able to collect this particular data in detail. Talking about the first, nothing but the rainfall. So in the rainfall measurement, we have studied about the various technologies about how we can able to measure the rainfall data. But these are the physical ways, like we are going to install the rain gauges at various locations and we can collect the information about at how much water depth is collected in by that particular rain gauge, that is representing the data of rainfall in the physical format. But what if some hilly areas are there or mountainous areas that are there? In that case, how we can collect the information about rainfall? So we have discussed about one technique, if you remember in the first unit, that is nothing but the radar technique. So this radar technique, ground-based radars, these are going to help us in the terms of collecting the aerial information. So ground-based radar offers the aerial measurement of the precipitation from a single location over the large areas in the near real time. So this particular radars, these particular radar beams, these are going to rotate about the vertical axis, measuring energy which is back scattered from the precipitation particles. Just in a similar manner, let's talking about the satellite image. The energy that is going to be coming or interacting with the objectives, this is going to reflect the energy back and which is sensed by the sensors. In a similar pattern, here we are having the radars. These are going to radiate the electromagnetic signals into the atmosphere, and when it is going to interact with this water molecule, it will be going to get reflected back. So this particular radar beam, which is rotating with the vertical axis, measuring the energy which is scattered back from the precipitation particles or the water particles above the ground above, and here we can have the extent of this aerial extent of this particular radars ranging from 50 to 100 kilometers or maybe more than that. So this rainfall intensity, that is related to the parameter which is called as the radar reflectivity factor with the empirical constant, that is calculated by the means of various studies. That's why we are going to say it's a empirical constant. So that is going to give us the value of the precipitation which is going to take place in that particular locality by the radar system. So this radar method cannot be used over the oceans or over the very large river catchments, but the aerial extent of 100 to 50, 150 kilometers square, we can definitely use this radar system in the terms of measurement of rainfall data. So the radar method is a part of your remote sensing information collection about the rainfall. So estimates, these are going to be made from the satellite imagery through indirect relationships between the solar radiance reflected by the clouds and the reflection and the precipitation. Again, this is the part of another method by which we can able to measure the rainfall data. So remote sensing techniques, if you will see, these are going to suffer from the some sort of errors which may be going to arise from the sampling. Ground-based radars, these are going to offer the little bit higher accuracy than the satellite techniques. Satellite techniques are going to be depending on what? These are going to be depending on the images which are captured with respect to the cloud cover. How much energy is reflected back from the clouds and the precipitation. From that some empirical relation is there, and that empirical relation is providing the data about the rainfall by the this remote sensing technique. But the actual data may vary with respect to the information that is calculated by these remote sensing techniques. That is the reason, if you are going to compare these two techniques, ground based radars or the measurement of rainfall through the remote sensing based on the reflective reflective waves from the clouds or the precipitation, solar radiance reflection by the clouds or the precipitation, these two methods, which is we can say approximately correct methods, but ground radar based for the smaller aerial extent, we can definitely say it is going to have a very less amount of errors. But if you are going to consider the areas which are larger than 10,000, so satellite techniques, these are capable of estimating the rainfall for such larger areas. For smaller areas, say 100 kilometer square, 150 kilometer square, these ground-based radar systems are going to be considered as an useful one. And the frequency of rainfall per minute, so smaller frequency is also calculated by this remote sensing technique, which is little we can say the not possible in the terms of your physical mode. Like if you are going to consider the rain gauges, so for the rain gauges you cannot, or you cannot get the readings or the information about what is the amount of precipitation falling per minute. So this particular information that can be provided by this remote sensing data or the we can say the radar systems about the rainfall. Okay, but if you're talking about the rainfall data in the physical format, like the actual measurement on the ground surface, you are getting the information about the rainfall per hours. So the frequency of data collection by the remote sensing, that is again more than that of the physical way. Only talking about the accuracy point of view, little bit accuracy is less as compared to the actual or the physical measurement of the rainfall data. That is the only concern about this remote sensing application for the rainfall measurement. Now the second parameter, that is nothing but called as the snow. So snow parameter is, again it is of interest to measure the snow. So the extent of snow or the ice cover or the snow water equivalent or the depth of snow, these are the various parameters. These are of much interest in the terms of water resources engineering field. So the snow cover extent, that is going to be monitored by the multispectral scanning in the visible and the nearly infrared region. Please remember this thing. Snow cover extent, that is going to be monitored by the multispectral scanning in the visible and the nearly infrared regions of the electromagnetic spectrum from the aircrafts or from the satellites. Gamma radiations, these are used to measure the snow water equivalent. In short, it is going to be written as SWE. So gamma radiations are used for the snow water equivalent. But the multispectral scanning in the visible and the nearly infrared regions, these are used to find out the snow cover, extent of the snow cover. So this snow water equivalent, that will be calculated using the relationship which is involving the gamma count and the soil moisture content. Snow water equivalent SWE, that will be calculated depending on the empirical relationship which is going to involve the gamma counts and the soil moisture content. Also, the sensitivity of the microwave radiations. So here we are having the combination of what? We are having the combination of visible, nearly infrared, which is denoted as NIR, That is, again, we are having the gamma rays, we are having the microwaves. So combination of all these things are going to be used in the terms of snow analysis. So microwave radiations, if you are going to consider, so the snow layers on the ground makes it possible to measure the snow extent, snow depth, and snow water equivalent by using the scanning multi-channel microwave radiometers from the satellites. So microwaves, these are going to be used commonly in the terms of identifying or the measuring the snow extent, snow depth, and the snow water equivalents. Okay, so these microwaves are going to be again considered as a very important. So the algorithms for deriving the snow depths and the snow water equivalents, these are going to be based on the generalized relationship which is involving the brightness, temperature of the snowpacks and the empirical constants. So this particular snow data, which is derived from the remotely sensing or the remote sensing technology, these are generally available in the public and the private domains for the various applications in the hydrology. Just like if you are going to consider the example of our Himalayan ranges, where we are supposed to take into account the hydrological models where there is a effect of snow melt. Okay, that snow melt which is resulting into the generation of runoff. So the models that we can develop with the help of this SWE calculation, where we can have a direct remote sensing input that is relating to the snow melt runoff forecasting. So for that purpose, again, this remote sensing is considered as a very important thing. The third parameter that we are talking about, nothing but the evaporation. So as I told you, evaporation, if you wanted to measure the evaporation directly, we can measure it on the ground by the means of pan evaporation. So various methods that we have discussed in unit number 1, these are the physical modes of measurement of evaporation. But how we can able to measure this evaporation by the means of remote sensing, so that we need to understand. So remote sensing, however, it is going to provide the information about the atmosphere or the land conditions. But these are not sufficient to estimate the evaporation. If you are going to consider the actual measurement of evaporation, that is directly going to give you the information about at what rate the water is getting reduced, water level is getting reduced into the pan evaporation. But through the satellite, we cannot able to measure at what level water level is getting reduced. So for that purpose, what we are doing, we are using some empirical methods, and we are going to measure the parameters which are involved into that empirical relations. So here we have discussed about some empirical relations, if you remember, in unit number 1. So there is one method which is called as a Penman-Montet method. Penman method, or the modified Penman method, or the Penman-Montet method. They are having the various equations, and in that equations which are derived, these are derived, or we can say these are the empirical relations. It will be consisting of various parameters. So these parameters we can measure by the means of remote sensing technology, and using that parameters we can able to calculate the rate of evaporation. So if you remember, one technique was there which is called as the heat balance method, heat balance equation, that will be going to be used to estimate the actual evaporation which is going to take place from the earth surface. And to use this heat balance equation, we required various parameters. Just like I told you earlier also, like we are supposed to consider the surface albedo, we have to consider the surface temperature, soil moisture, vapor concentration, surface emissivity, net radiation, air temperature, leaf area index, fractional vegetation cover, aerodynamics, roughness length, aerodynamic resistance for heat, and aerodynamic resistance for vapor transfer. Many of the parameters we have we are listening first time, many of the parameters that we really don't know, but these are some of the parameters which is a part of your methodology. These are need to be calculated if we are supposed to use this heat balance method for estimating evaporation from the surface. Okay, so estimating evaporation through modeling, it is going to require the accurate observation of the wide range of land surface variables. So here we are listed around 13 various parameters, and if you are able to calculate accurately all these parameters, then and then only we can able to get the we can say the little bit accurate evaporation data. So the remote sensing estimates of the evaporation are considered as sufficiently accurate to the relatively homogeneous land surface when all necessary meteorological variables are measured. Just give me a moment. So remote sensing estimates are very accurate, we can say, if we are able to measure all these parameters. So this is about the third hydrological parameter, that is nothing but your evaporation. Now one more, we can say we are having the soil moisture. Now soil moisture, why it is required? The soil moisture is required for the purpose of your infiltration rate. So soil moisture, that is going to interfere between the earth surface and the atmosphere. So it is important parameter that connects the water that is present into the atmosphere, that is a part of evaporation, that is also going to be connected with the water within the earth, that is nothing but the infiltration, and the water that is flowing over the surface as a part of surface runoff. So as important as this parameter seems, it has not found much applications because it must be measured not at the single point but at the multiple times and at multiple locations. So this particular variable in space and time, since the moisture exhibits a large spatial and temporal variability, and that is the reason we cannot make the use of the soil moisture content more in the terms of hydrological modeling. But the point data, that is the soil moisture at any particular place, that can be remotely measured using the different parts of electromagnetic spectrum. So the gamma radiation technique, this is the technique which is going to be used by detecting the difference level between the terrestrial gamma radiation flux of wet and dry soil. So the reflected solar radiation in the visible and nearly infrared VIS and NIR, visible and nearly infrared regions, is not particularly useful in estimating the soil moisture. It is the microwave region. It is the microwave region of the spectrum that offers more attractive techniques to estimate soil moisture under a variety of the topographic and the land cover conditions. So soil moisture, if you wanted to calculate, if you are interested, the visible and nearly infrared areas, these are not sufficient, but you are supposed to go for increasing the wavelength to the microwave region, and through that we can able to get the data about the soil moisture. So this is the fourth parameter. Now the next, talking about the surface water. Now the water which is flowing over the surface, that is nothing but the part of your surface water. So there are three aspects of the surface water that you need to take into account. One, locating or delineating the surface water boundaries. Like if you are going to consider, say, lakes or the ponds, so to mark that particular line, that boundary, that is the one part of assessment in the terms of hydrology, locating or delineating the surface water boundaries. Second one, measuring the surface water levels. What is the depth of water level in that particular water boundary, in that particular water, we can say the source. So that is the measurement of water levels or the depth. Ascertaining the river flows or the runoff. So these are the parameters, or these are the three aspects that we need to study in the part of water assessment. So the remote sensing in the visible and nearly infrared, NIR. These are the regions these can easily locate and delineate the surface waters. So the first parameter, if you wanted to carry out the study of this, you can use the visible range or the nearly infrared range in the electromagnetic spectrum. Lakes and river levels, that is the water depth, this can be measured within the centimeters of accuracy by the means of radar altimeters on board aircraft and the satellites. And the third parameter, that is surface level monitoring, if you wanted to carry out for the runoffs, that can be done indirectly by using the remotely sensed data as inputs along with the ground based data to simulate lake and the river levels of the flows. So combination of these two, that is the physical method and the remotely sensed information, that can be make the sense in the terms of ascertaining the river flow or the runoff which is going to take place from the rivers. So surface level monitoring can be done indirectly by using the remotely sensed data as well as the inputs what you are getting from the ground based study. That is nothing but you are taking the information from the gauge discharge locations. So that is nothing but a part of your surface water measurement. Then if you are going to talk about only runoff, so remote sensing information or this remote sensing technique, this particular technique cannot measure the runoff directly. Please remember this particular line. This is very important line. Remote sensing cannot measure the runoff directly, but the information which is derived from the remote sensing, that can be used to estimate the runoff in a various ways. So how we can make the use of this remote sensing data for measurement of runoff? The first point, the Natural Resource Conservation Service, NRCS, National Resources Conservation Service, NRCS, these are going to utilize a technique or a method. That method is nothing but called as the curve number method. Okay, which is called as the SCSCN. Okay, SCSCN or NRCSCN. NRCSCN. SCSCN or the NRCSCN, these are the methods which are used for the estimation of runoff. So curve numbers, these are going to be based on the land cover, land use, soil types and the moisture conditions. So this particular data, these are conveniently obtained by the remote sensing. So this is the one way of measurement of runoff, that is by using some specific method we can able to calculate, and that for that method whatever the data that is required, that we can get from the remote sensing technique. That is the one way. Second approach or the second method, that is watershed topographic features and the drainage pattern, these are easily ascertained from the good imagery. So this particular information can be used in empirical formulas to estimate the runoff. Simple. Okay. The third method, where this remote sensing is going to be considered as a quite convenient to a certain basin area. Basin refers to the catchment. Okay, basin refers to the catchment. So we can able to calculate the catchment area and the drainage characteristics. Now what are the drainage characteristics? It refers to what? It refers to the network of valley lines. Network of valley lines. So if you are having the network of valley lines, you can able to find out the tributaries, small tributaries, which are conveying the water from the various regions and contributing it to the main river. So drainage characteristics, that is nothing but the network of valley lines that you can able to estimate from the remote sensing data. So mapping of the aerial extent of flooding and the delineation of the floodplains, that has effectively been done using the remote sensing data. So this is the way by which we can able to make the application of remote sensing in the terms of determining the surface water flows, that is nothing but the runoff. And one more parameter, that is nothing but the groundwater. So remote sensing device record features on the earth surface. But what about the groundwater? Groundwater is nothing but the subsurface phenomena. So information on the groundwater cannot be obtained directly by the means of remote sensing technique. Again the same sentence what we are repeating for the surface runoff. So groundwater, as it is a subsurface phenomena, information on the groundwater that cannot be directly estimated or that cannot be obtained directly from the ground remote sensing technique. So there is a technique called as a aeromagnetic surveys or the microwave imagery that can provide the some penetration below the earth surface, but these are of limited values to the hydrologist and more applicable to the simple geology and very shallow water tables. Not even if you are going to say about the unconfined aquifer, so confined to chhod do. Only about the unconfined aquifer, a part of unconfined aquifer, that study that we can able to carry out with the help of aeromagnetic surveys or the microwave imagery. So information on the groundwater is assessed by computerizing the hydrogeology of the region by merging the satellite image and the data which is available on field for the geophysical data. So what we can do, so for that purpose, if say we are having the satellite data for the terrain, we are supposed to overlay the data for the geological features of that particular locality. Say like any particular locality is having a particular kind of a soil or the particular kind of a rocks. So on the similar platform or that particular image of the soil data, we are supposed to provide the geophysical information, like in this particular area which that this particular kind of a soil is present at this particular depth. Okay, so just like the topo sheets are prepared, the geophysical maps, these are prepared by the Geological Survey Department of India, that is GSDA. So this geophysical data, this is going to be used, or this can be used along with the terrain data, and by overlaying these particular data together, we can able to use this in the terms of modeling. So once the conceptual model is completed, this remotely sensed data that can be used to assess the upper boundary conditions, namely the recharge, evapotranspiration loss and the groundwater drafts for the irrigation, that can be done by the means of remote sensing applications. So groundwater that cannot be calculated directly, but by the means of the geophysical information, the geophysical maps along with the terrain maps, that we can make the use together in the terms of study of a groundwater hydrology. So this is how we can able to relate the remote sensing with respect to the another hydrological element, that is nothing but the groundwater. Okay, so till now what we have covered, again I would like to recall from the content part. Till now what we have discussed, so we have covered in detail about the principles of remote sensing. We have covered the integration of remote sensing with the GIS, and we have covered the remote sensing of the hydrological elements. So these three topics we have covered in detail till now. Okay, now we are supposed to study about the remote sensing applications to the hydrology, introduction to the computer models for the hydrology, and rainfall runoff or the flood flow models that we need to understand. Okay, so I will continue with this particular point related to the applications to hydrology in the next session. Okay, so we will stop here. If you are having some questions or doubts, please let me know. I know this is a little bit more theoretical things that we are discussing about this remote sensing and the hydrology, but this is a very important part that you need to understand. So in the next session, we will discuss about this remote sensing applications to the hydrology. Along with that, we will cover the various computer models which are used in the terms of hydrology. Okay, so computer models which are used for the watershed hydrology, that statistical models are some of the models which are the stochastic models that we will discuss how we can able to make the use of this. We will also list down some of the hydraulic models, how we can able to use this for the reservoir planning or the hydrological studies. Okay, for flood flow analysis, flood frequency analysis, that we will discuss in our next session. Okay, any questions till now? So I'll be going to share the recording of this session. So some of the students, those who are not present, they can go through this particular recorded session in the maybe whenever they are getting the time. So till now I will be downloading the attendance. If you are having some questions, you can just unmute and ask the questions. No? Okay, no issues. So we'll be going to stop here. Okay.